Okay, so I'll give you, I think Thursday I can get you a day in the lab. I moved the due dates back on 3/4 till Sunday, so I'll give you some extra time to that's a big assignment, kind of work through that. 3/3, I think I'll give you until tomorrow night. But you do need to be, my expectation is that you're not gonna have a lot of class time this week, but you gotta be cranking away on those, on your own time. If I need to get you into TA, just let me know. I'm happy to do that. So also at the end of the period, I'll see if anybody needs that. Yeah, Paisley. Where's Paisley? Paisley right there. Okay, so what I want to do today, let's kind of finish up some 3-5 stuff. And what's nice about this is 3-5 is really ends up being really simple. 3-5 mostly deals with how do we find horizontal asymptotes of rational functions, and we can do it by inspection. We don't even have to do anything, right? Come up with kind of a set of guidelines to say if it looks like this, this is the result. If it looks like this, this is etc. And we'll get to that in short order. And then there's one other kind of slightly odd interpretation of a rational function that we're going to look at too, that involves some radicals. But it's not that big a deal. This is the one that we looked at yesterday. Now our strategy yesterday, which is a really good one, was we looked at the numerator and the denominator separately, and in the limit, remember we're talking about the end behavior of a function deals with limits at infinity. It doesn't matter if it's positive infinity or negative infinity. It's long ways in that direction or long ways in that direction. Same idea though. Remember that we talked about the end behavior of a polynomial is that the leading term is always the dominant term when we talk about end behavior. Whatever has the highest power of x is the only term that matters as x gets really big in either the positive or negative direction. And so we were able to just kind of do that, right? And look at the ratio of those two terms. And that's an easy one. Algebraically, the x's cancel, and that's probably the best and most efficient way of doing a problem like this. There's another technique that I'm just going to introduce. I mean, it's not a big deal. We'll look at maybe just one other way of approaching this that will apply in some other situations also. You could also do something like this. You could say, and something else I don't think I did, I should do. What is a rational function, by the way? What's a rational function? Because that's primarily what we're concerned with here. Rational functions. Good to know what these are. So a rational function, r of x, could equal something like f of x over g of x, where f of x and g of x are polynomials. So it's just a ratio of polynomials. That's when we talk about a rational function, that's what we mean. Okay? So the other thing we could do here is we could just factor out the biggest power of x that we see in either the top or the bottom if we've got a rational function. So in this case, I've got x squareds in the top and x squareds in the bottom. And so if I just factored an x squared out of the top and bottom, what would I get? So if I take an x squared out of the top, what am I left with? If I divide an x squared out of both terms. First term I'm going to get 3 minus. Yeah, does everybody see that? Because if I factor out an x squared from 2, I'm dividing that away. I'm either left with 2x to the minus 2, or even easier. Remember, factoring is a process of division. So I'm really literally just dividing each of these terms by x squared to pull that x squared out front. Just write it like that, 2 over x squared. Okay. So that's what we get in the numerator. In the denominator, if I pull out an x squared, I get something very similar, right? I'm going to get 2 plus 3 over x squared. And in the limit, as x goes to infinity, well, first of all, the x squareds cancel, top and bottom. And then the limit of any term that's got an x squared in the denominator is going to do what? So for example, this guy and this guy, what's going to happen to them as x explodes? What do we say happened to a fraction as the bottom gets huge? Yeah, it gets smaller. It goes to 0. And here's a good way to show that. Those vanish. They go to 0. And so, does he do that too? Yeah. And so you end up with 3 halves. Okay? Okay, so there's one problem to look at. That's the same result we got yesterday, right? Okay.
Why don't we do this?
Say it again?
Why don't we do this before that?
Well, I like the other way better myself. It's because if I mean, they're just different. We're doing the same thing essentially, but just algebraically taking a slightly different approach. The other way, remember what we said was, we know that in the limit that x is going, the limit that x is going to infinity. I thought this was kind of slick. We know x is going to infinity. We know that all but the dominant terms are going to vanish in that limit, and so this, this complicated. Well, it's not that complicated, but this rational function just devolves to a ratio of the leading terms, which is algebraically pretty easy to deal with, right? Seems like that's even easier to me. You don't even have to factor anything, right? But either way, I mean, it's either way. So what about, you take your pick. Either technique. Let's look at this one. Same idea. Looks very similar, but notice that I've got an x squared on the bottom this time, and just an x on the top. Okay, so one thing we could do, right? We could factor out an x squared like we did before. Maybe this one will do both ways, and after that, you just take a pick. Being this is fresh in our minds, how about we just do what we just did first? So if I factor out an x squared, because that's the biggest power of x I see in the top or the bottom, on the bottom, it looks just like it did last time. In fact, it's the very same numerator we had before, right? So if I take out an x squared, I've got 2 plus 3 over x squared. Now what about the top? If I take out an x squared, what am I left with?
3 divided by x. Take away 2 divided by x.
Yeah, 3 divided by x minus 2 divided by x squared. And the x squareds cancel algebraically, right? And so now what? That term vanishes just like before. That term vanishes, but even that term vanishes, right? And so I just end up getting 0 over 2, which is 0, right? If I look at it the other way, if I were just to write this as the limit of the leading dominant terms, well, an x cancels there and an x cancels there, and I get the limit of 3 over 2x as x goes to 0. What's that do? I mean, as x goes to infinity. Gosh. And so I got a fraction with the bottom exploding there. Everybody see that? And so that one's just going to go to, by the same rule, that one's just going to go to 0. And so I get 0 either way. Right? Okay, now let's look at, and really what we've done here, they're specific examples, but they're representative of general cases. We looked at a case before where a rational function where the order of the numerator and denominator were equal. It doesn't matter that they're squared. That could have been x to the 10th and x to the 10th. The answer would have been the same, right? So if the polynomials top and bottom are of the same order, we got this kind of result. And we'll come back and try to compile this into just a case by case, prediction. What's going to happen when, in this case, where bottom was a bigger order than top, and then the only one left to consider would be, what if the top is a bigger order than the bottom? Okay, something like that. Okay, so take your pick. I don't care which technique you use. Probably the easiest to just, I don't know, it doesn't matter. If we just look at the ratios of the leading coefficients, how about? Or leading terms. Ignore those guys and we get 3x cubed over 2x as x approaches infinity. We can cancel a little bit. I can cancel one of the x's, top and bottom, leave me with the limit of 3x squared over 2 as x approaches infinity. And what's that? Think about that. What is it? Oh, yeah, it is, isn't it, right? Because if I've got, really this is just 3/2, some constant times x squared. As x approaches infinity, obviously x squared is approaching infinity even faster, right? And so this one's blowing up, okay? Does that make sense? Okay, so this is one where, I mean, we could say no limit, we could say, in this case, being as it's positive infinity squared, we know it would be positive infinity, okay? But that's, we get a different result in that case. So now let's generalize this. What's gonna happen if we wanna write this, see if we can break this down into 3 possible cases. So limits, or end behavior, let's call it. End behavior of rational functions. Case 1. What were these? P and Q, I think, in the book. I don't even remember. So we're taking a limit of a rational function where P of x and Q of x are same order. What happened there? We go back and look at that case. Three over two, okay. So it was just the ratio of the leading coefficients. That was it, right? When the powers of x matched up, the highest powers of x matched up top and bottom, all we had to do was just look at the ratio of the leading coefficients, and that's our answer. Is that a horizontal asymptote? We got the answer. The limit was 3/2. Is that a horizontal asymptote if the limit is constant at the tails? Yeah, it is, isn't it? This gives us the horizontal asymptote y equals 3/2, right? So we did get one. So case 1, same order we got. Horizontal asymptote at y equals ratio of leading coefficients. Okay, and that's easy. We can just look at it and see. There's no math to do. Just by inspecting, we know that that's going to happen. What happened in case number 2? Where, where the bottom was higher order polynomial than the top, bigger power of x in the denominator. Went to 0. Is that a horizontal asymptote? The limit is constant, right? Yeah, it is. In fact, in this case, the horizontal asymptote is just the x-axis, right? It's just the line y equals 0. So yeah, horizontal asymptote at y equals 0 every time. And so pretty slick. Once again, we got, just by inspection, we get our answer. We don't have to do anything. Same order, top and bottom, horizontal asymptote at y equals 0 every time. And then the last case, if the top is, oops, not go anywhere, it's on that page. If the top is higher order than the bottom, what happened? Do we get a horizontal asymptote? No, no asymptotes there. Okay. That's one where we're going to get end behavior that's going to be, it's going to be infinite. And we may want to take advantage of that. In fact, in 3.6, we're going to look at the case if the numerator is exactly 1 degree higher, let me say this in a better way. If the exponent in the numerator is exactly 1 higher than the exponent in the denominator, then it turns out that it's not going to give us a horizontal asymptote. It's going to be infinite tails on the function, but turns out in that case it's going to follow a slanted linear asymptote, which we actually call a slant asymptote, which is useful to know too. That didn't happen here, but we found out that as we approached positive infinity, the sign, at least we knew that it was sloping upward forever. Okay, so, but not a horizontal asymptote. So if the top is of higher order, then no horizontal asymptote. Okay? That makes it pretty easy. Now the sort of the weird case that they throw at you a little bit is something like that. Okay, but we can be really tricky about this too. And this isn't really the way the book approaches it, but this is a good way to do it. What if we're trying to deal with something like the limit of the square root of 3x squared minus 2 divided, or excuse me, it's just the polynomial 3x squared minus 2 over the square root of 2x squared plus 3. And I don't, you know what, I think I want to change that a little bit. I want to make that, I do want to change that just a little bit. Let me do, there. Okay, that's better. Okay, so what about this? Any suggestions how we could deal with this? And the hint I'll give you, what do you think?
With the denominator, raise it to that half power instead of using the square root.
Okay, we could, yeah. And think of it that way. The denominator, if it's a square root, it's to the 1/2 power. Okay. Now, is there a way? I want you to see that the original technique was kind of handy, right? When we just said in the limit that x is approaching positive infinity, the dominant term of the polynomial is going to be just the leading term, right? So see if we can take advantage of that. The top. So in that case, if we're going to infinity and we're just looking at the dominant term, what's the top going to degrade to? 3x, right? Okay. So that's easy. That's just like before. What about the bottom?
Doesn't it just go to 2x and square root of squared?
Ah, okay, good. So we're looking, the bottom is going to degrade to just the limit of the square root of 2x squared, right? And the square root of 2 part, we can just take out front, because I can think of the square root of 2x squared as the square root of 2 times the square root of x squared. So I could at least do this. And what is this equal to? Be careful with this. What is the square root of x squared? My definition. This is one that, maybe it doesn't jump out at you yet, but I want it to. By the end of the year, it needs to. What is it? It's not just x. Kind of-ish, plus or minus. Now think about this. The square root of x squared. Let's just test it out. What if I put in 3? If I put in 3 for x, I'm going to get the square root of 9, which is 3. It seems to just be x. Put in 3, I get out 3, right? But what if I put in negative 3? I get positive back, don't I? Because negative 3 squared is 9. The square root of 9 is 3. What does that sound like? Absolute value. Okay? Right? So that is the best, most fundamental definition of absolute value of x is the square root of x squared. It's better than, piecewise function describes what its graph looks like, but this really describes the character of it, what it really does, right? So then this ends up looking like the limit of 3 over the square root of 2 times x over the absolute value of x. Okay. Now let's focus on that last part for just a second, because that's something that comes up surprisingly often in math. A function like that. If we look at x divided by the square root of x, or the square root of x over x, they equal the same thing. What's that gonna do? Let's just think about that. When x, in fact, let's make it a piecewise function. When x is positive valued, what's that gonna do? It's gonna be, it could be positive what, exactly? If x is positive valued, what's the square root of x equal to? Well, it's just positive x, right? And so I'm gonna get x over x. Does that make sense? In the event that x is positive, the absolute value of x doesn't change anything. It's just x. And so I get back an answer of 1. Okay? What if x is negative valued? If x is negative valued, the absolute value of x is equal to negative x, right? Everybody, right? And so this looks like negative x over x, which is negative 1, right? Is it defined at 0?
No.
Not defined at 0, correct. How come? Can't divide by 0, yeah. So it's undefined there, right? So if I look at a graph of this thing, it always looks the same. It just looks like this, right? I've got makes sense? Okay, so the answer to this one then, if we're approaching positive infinity, x is clearly positive valued. And so this part right here is just going to be replaced by 1. Right? And so the answer to this first limit up here is just 3 over the square root of 2. Okay, what's the only difference in the bottom case? Yeah, x is negative valued there, right? And so it's just going to mean that the absolute value of x over x, or x over the absolute value of x, same deal, is going to give us back in the bottom case, it's going to give us back a negative 1. So the only work you got to do here, and which coincides with the way you might want to think about this, is just writing it like this, the limit of 3 over the square root of 2. There's the ratio of my leading coefficients, so to speak, right? And then I've got this x over absolute value of x part that we know is always going to look like this. Right? So we just get back, this is going to go in this case to negative 1, and I get back negative 3 over root 2. And that's a pretty easy, compact way of doing the work. Okay? Does that make sense? Okay. All right. How are we doing? I don't think there's really anything else of major importance that comes up. And 3-5. I think that's about it. Being as we're here today, why don't we maybe, I'll throw it out for questions on other stuff. Yeah.
Can you do some of the trig ones on 3-4?
Sure. Yeah, you bet. Let's do that.
They're out of the book.
Oh, okay, good. Makes it easy. Okay, do you know what numbers?
1 on 50, I think.
50, okay. Oh, there's another one here I want to do too. Yeah, there's another one I think that's a good one. Okay. $50 doesn't look. Trig one. Okay, so it's like 36 and 34. 32 probably, right? Let's do 33. That's a good one. It's a good practice one. Okay, so there's the problem. We're supposed to just find everything. Find relative extrema and points of inflection. So, what are we gonna do? What do we always do if we're analyzing? We're using calculus to find relative extreme. Take derivative. So first we gotta take the first derivative. So what's the derivative, using chain rule, what's the derivative of secant something? Secant tangent. And then the derivative of the argument of the trig function, if I look inside, what's the derivative of x minus pi halves? 1. Okay, so the chain rule didn't really end up being that important. So there's our first derivative, okay? Well, let's go ahead and, while we're there, let's go ahead and analyze this. So secant tangent, now, on our domain, we gotta find the critical numbers. So just, let's kind of be systematic about this. Remind me, where do we look for first derivative critical numbers? Where the derivative is 0, okay, or undefined. Let's take care of the undefined first, because that's the one, just get it out of the way. That's the one we sometimes forget. So first derivative would be undefined where? Now, we have to be a little careful with this because I've got secants and tangents this time, not sines and cosines, and secants and tangents do have vertical asymptotes. There are places where they're undefined. What I like to do is this, I always write these in terms of sines and cosines, so I know, I know what am I looking for. Is what the denominator of the fraction here. If I write secant, for example, secant is what? 1 over cosine. So I get 1 over cosine x minus pi halves times sine over cosine. Right? And if I could even multiply those out and just get sine of x minus pi halves over cosine squared. So where is this thing going to be undefined then? Where do we have to be careful about looking? Where what is equal to 0? Cosine. Okay. So wherever cosine of hand is equal to 0, this thing is going to be undefined. Right? So cosine of x minus pi halves equals 0. And remember, when we're solving trig equations like that, we just want to look at the unit circle, right? In this case, we want to know where is the cosine function equal to 0. Let's remind ourselves. So, where is cosine equal to 0? That x or y component? It's going to be y component, isn't it? Right? So it's going to be on the unit circle there and there, right? Now our domain, well, okay, so pi halves and 3 halves pi. What are we going to be setting equal to pi halves and 3 halves pi then? Because all the cosine cares about is the angles that you're feeding. When you feed it a pi halves, it's going to be 0. When you feed it a 3 halves pi, it's going to be 0 also. Doesn't care where those are coming from. We could have the most complicated function in the world inside the cosine. It doesn't care. It just wants to know what angle you're giving it. So what are we setting equal to pi halves here then? Right? If the cosine, let me say that again. If the cosine, when would the cosine see an angle of pi halves? We don't yet know what that would make x. Does that make x pi halves? No. Because the x, we're subtracting pi halves from x inside the cosine function. Does that make sense? So you almost want to think about it, and this is going to get more comfortable for you as we get into chapter 4, but a good way to think about this is in terms of a variable substitution. A lot of times, especially when these things start to get really complicated, you get layers and layers of functions, just call that theta. Whatever is inside the cosine, call it theta, right? When theta equals pi halves, we're going to have problems. So it's undefined when theta equals pi halves or theta equals 3 halves pi, right? What's theta? Well, theta is x minus pi halves in terms of our variable x, right? In our original domain, if we look back up, or if I sneak up here a little bit, the original function, look, we have this restriction on the domain. what is restricted to be greater than 0 and less than 4 pi there, specifically? Well, what does that domain refer to? Values of what? X, right? Because x is the variable in our function. You see where I'm going with this? That's in terms of x, but the cosine is really just cares about the whole thing. It cares about what we call theta. So now we've got to relate the variable x, which is the variable of our function, to the places where the cosine function is undefined. So then we just do that like this. We'll say instead of theta, we'll call that x minus pi halves. And solve for x. We just ask the question, when does our angle x minus pi halves equal pi halves? When? When x equals what? If I solve for x there, what do I get? Pi, sure. Okay, so when x equals pi, theta equals pi halves, right? So that's one place where we're going to have problems. What if we do this one up here? Well, if we say x equals, whoops, sorry, x minus pi halves equals 3 halves pi. What do we get there? 2 pi. Okay. If I add pi halves to that. Could we have missed a spot? Are the only two places where cosine goes to 0 pi halves and 3 halves pi? Sure, because look, our domain, x is extending clear from 0 up to 4 pi. We can take multiple laps around the unit circle, right? We just know that these locations, the location here on the unit circle refers to pi halves plus 2n pi, doesn't it, right? And this one down here is really 3 halves pi plus 2n pi. I could do any multiple of full laps around the unit circle, and every time I make a lap, when I get down there or up there, those are places where cosine equals 0, right? So we'd really have to look at some other ones too, wouldn't we? Now, so we might want to look at 5 halves pi, for example. That was a suggestion. Okay, so what happens if we got those two answers? If x minus pi halves equals 5 halves pi, and I solve for x, what does that give me? 3 pi. If I add pi half, I get what, 6 halves pi, which would be 3 pi. Okay, what if I tried x, gosh, keep doing that, x minus pi halves equals, next one down here would be what, 7 halves pi? Everybody agree? On our second lap, okay. If I add pi halves to both sides there, what do I get? 4 pi. Is that part of my domain? Okay, yeah, that one's not, is it? Because we didn't actually include 4 pi. So it looks like we've gone far enough in that direction. We can lose that one. That's not in our domain. We might want to go backwards a little bit though, just to make sure, right? We started at 0 and went to pi halves, 3 halves pi, 5 halves pi, 7 halves pi, but we could have started at 0 and gone backwards to negative pi halves, right? So what if I do that? What if I start with
It's
x?
not in the domain.
It's not going to be, is it? What's that? What's not in the domain? Okay, but hang on. But remember the domain. Now, there's two. I was curious to know why, because maybe someone's seeing ahead and seeing that it's not going to work, because it actually isn't. But you don't know that immediately, because the domain. Remember, this is the domain for x, not for x minus pi half. Does that make sense? So we got to be careful with that. Just because my how do I want to say this? Just because my domain of x doesn't include negative pi halves doesn't mean that the angle that cosine is seeing that we called theta couldn't be negative pi halves, right? Okay, and it turns out, I'm assuming people probably just worked ahead a step and said, oh, it's not going to work, which it doesn't. Because if I set x minus pi halves equal to pi halves, and did I do that right? Negative pi halves, sorry. If I add pi halves to both sides, what do I get? 0. Which is not included, that's right. So it didn't work. But if that endpoint had been included, it would have, right? Well, there would have been an endpoint. So we can get rid of that one also. Make sense? So we got 3. Now, what if the domain had gone from 0 to 20 pi instead of 0 to 4 pi? Can you see that that would have been pretty tedious? It would have been pretty tedious, wouldn't it? Is there a better way we maybe could have done this that we could have avoided having to just try discrete values?
Could you just graph it with the zeros?
We could. If this were a graphing calculator test, that would be a great plan, and that'd be the best way to do it by far. What if we didn't have our graphing calculators? Is there a way we could have done this where we wouldn't have to, if you understand my question, we don't have to look at specific examples of what theta could be? Could we have set this up in terms of just generally, like in terms of maybe n or something? Okay. How do we generally say these 2 points, all infinite values they could take on the infinite laps that an ant could take around the unit circle? Instead of just relegating ourselves to just 1 lap or 2 laps, what if we said, how do we say that and that combined? It's something that's like that, isn't it? It's like pi halves is right here, but if I advance to this first one, pi halves, then how do I get to the second one? Or this one? What do I always do? To get from there to there, how far am I traveling? Pi. To get from there, clear around to there, I'm just traveling 2 pi. To get from there backwards to here, I'm just subtracting pi. If I go around a whole bunch of times, does that make sense? I'm just always going to be adding some integer multiple of pi to my starting point. Right? So I could say both of these things combined by just saying they always equal, not x, theta equals what we call theta, right, is equal to pi halves plus n pi, right? And why not just solve it in terms of n? And then we could just see which values of n give us answers within our restricted domain, right? So what's that going to look like? Well, we would have said pi halves plus n pi. When is that equal to, what was it, x minus pi halves? Is that what our argument was, what our angle was? Right? We were taking the cosine of that, weren't we? Right? That's hand, cosine of hand. Whenever it equals that, whenever we're taking the cosine of equals that, we're going to have asymptotes. So how would we solve this for x? Yeah, good. I'm just going to add pi halves to both sides. So that's going to give me pi halves plus pi halves is just pi plus n pi. That's pretty slick, right? So I get pi plus n pi. N could be any integer. So if we know that x is restricted to be between 0 and 4 pi, well then, that's going to give us, if n is an integer number of pi, the only ones we're going to get are going to be pi, 2 pi, and 3 pi, right? But if n had gone or if our domain had gone from 0 to 20 pi, we would have kept all the values that, all the integer multiples between 0 and 20 pi. We would have to check them all then. We would have just known right away, okay, we're getting values of x every integer multiple of pi. See how that works? Much better way to do it if you're doing lots of them. Okay? So back to our problem. So we found our critical numbers. It's undefined, pi, 2 pi, and 3 pi. Now we got to go up and take our equation right here. I'll just grab all this stuff and go to the next page and set it equal to 0.
You want to know in 5 minutes? Or?
Oh, okay. So we're done with this. We'll come back to this. Okay, here's Here's my challenge problem. They are, I know. Did you ever think you'd be seeing problems that take so many pages to do? It's the greatest feeling that once you just really get this stuff, it's just awesome to look back and see pages of work and say, man, I get all that. That makes sense. It takes a while to get there, but you guys are doing great. Here's my challenge problem. So I want you to see if you can resolve this little situation. These two mathematicians haven't seen each other in a long time. They meet on an elevator and they're getting talking. Oh, I'm doing great. How you doing? Wonderful. Yeah. How's your family? Oh, great. You have 3 kids, right? One of them says. And he says, yeah, I do. Yeah. Now, how old are they again? I can't remember their ages. And being mathematicians, they're kind of going to challenge each other a little bit. The other one says, well, I'll tell you this. The product of their ages is 36. And the sum of their ages is equal to the number of floors on this elevator, points over the elevator. And the second mathematician looks over there and says, that's not enough information. So the first one says, oh, yeah, you're right, all right. Well, my oldest has red hair. And then the other mathematician says, got it. Okay. So I'll say it one more time, please. I want you to see if you can come up with the ages. How old are they? How old are you? I'm not going to tell you. You don't have to know. No. The product. So, I won't go through the whole litany here, but the one mathematician acknowledges that she has 3 kids, but she's not going to tell you the ages. I'll just tell you this though: the product of the 3 ages is 36, and their sum is equal to the number of floors on the elevator. She points to.
Do we know that?
No, I'm not going to tell you. You don't need to know.
But they do that.
But it doesn't matter. Doesn't matter. You don't need to know it. Here's what you need to know, though. What you need to know is that when the first math, and these guys are both these mathematicians are smart, so they're doing this correctly. The mathematician looks at the number on the elevator and says, I made some calculations. That's not enough information. That's important to know. But when the other person says, oh yeah, you're right, but my oldest has red hair, that's enough. All of a sudden now, that makes it doable, and he knows the ages of her kids. Yeah? Okay. Oh, and of course, does it matter that it's red hair? No, it could have been black hair. Could have been. That part doesn't really matter, that it's red hair. That's not crucial. I'll give you that. Okay.
I know.